Hello everyone. This presentation is about how we can use FME in the extraction of 3D buildings from point cloud data, with a focus on the challenges on processing large datasets with a 3D component. First, let me introduce myself. I'm Bert Meus. I live in Belgium, close to the small historical city of Leuven. I have a background in bioengineering and Earth observation at the KU Leuven University. Now I'm working for about 12 years in the company GIM as an analyst in GIS and Earth observation. For those who do not know GIM, we are a private company and an expert in everything related to geographic information. I'm working a lot on remote sensing related projects as well as projects with a focus on GIS. I started using FME for simple tasks such as converting KML files to shapefiles and the other way around, and gradually came to know that the software is a very powerful tool to process GIS data and is relatively easy to use even if you don't have a lot of scripting and programming skills like me. Let's give an overview of what I will be talking about today. First, I will give some background information about why we did this project. Then I will discuss the objectives and give a small overview of the methodology. Then I will focus on 3 specific challenges in the project where we used the FME software, and I will end with some conclusions. It's time for a statement. Life is better in 3D. Movies are better in 3D, a lot of video games are now in 3D, and even our World Fair roller coaster that you see here in the background would only be dull if it would be a flat one. In our company, we focus on GIS, but usually we only do that in 2 dimensions, X and Y. It's not that we do not want to go to the 3rd dimension, but usually the required input data is missing. This is what we want to change with this project, to add the 3rd dimension to the data that we use, and more specifically to our building data. And that leads us to our geodata product that we as GIM are very proud of, Belmap. In Belgium, although it's a relatively small country, our geopolitical situation is a mess and we even have 6 different governments. This causes that most of our geodata are produced and maintained at a regional level and are not aligned at all with each other. Belmap combines the best quality location data from more than 20 sources and bundles this data in 7 clear themes, which you can see in the figure. It is a database with more than 5 million addresses and more than 7 million buildings in Belgium with a lot of extra information attached to them, and includes a portal and an API service. Recently, we also expanded the product to the Netherlands and Luxembourg. Here we will focus on the building component of Belmap in Belgium. Up to now, the Belmap buildings were present as 2D footprint polygons. In the figure on the left, which shows the definition of the different LOD standards, this is a level of detail 0 or LOD 0. So the buildings are present as simple flat 2D polygons. Within Belmap, we have the building height as an attribute in our 3D component, so we could go to LOD1 if needed. LOD1 is a box representation of the building with a flat roof. Let's take a look at the other LOD standards. In level of detail 2, the buildings are represented as a building model with standard roof structures present. LOD3 adds more detail to the building representation. In LOD4, also the interior features such as interior walls are present. This project is to take our Belmap product to LOD2, so to move away from the flat LOD0 model and also the LOD1 block model, and to have more realistic representation of the building in 3D. For this, we use LIDAR point cloud data, which are made available for free by the regional sources. Let's go quickly over the methodology. First, we do some pre-processing on the point cloud data. Then, we use a specific tool to extract the 3D roof polygons from the LIDAR data. The outlines of the roof polygons are then matched to our Belmap building footprints, and in the same time, heavy geometrical corrections are performed. Also, the Belmap ID is added so it can be linked to our other Belmap components. Walls are added, and an output in a specific format is created so we can visualize and use the LOD2 model of each building in Belgium. For most of these steps, FME was chosen as the most suitable tool to work with. Only the extraction of the 3D roof polygons from the point cloud data required another specific tool. Let us already have a sneak peek at how the result will look like. This screenshot shows a house in a residential neighborhood. You see that we also managed to produce an LOD2 shape also for the smaller annex buildings such as garages and garden sheds. The first challenge I will discuss is the pre-processing of the LIDAR point clouds. We received different LIDAR point cloud data for the two major regions in Belgium, Flanders and Wallonia. The data for Flanders also covered the capital region of Brussels. Mainly for Flanders, the northern part of Belgium, the input data were really huge. There's over 30 terabytes of data for Flanders, delivered in hundreds of thousands of individual tiny point cloud files. This is of course way too much data to be processed in one go, and also the large number of files and the way they were structured was problematic. For the next step, point cloud tiles of a manageable size are required, so we need to do some pre-processing. For this task, we used FME. FME allowed us to transform the bunch of unstructured LIDAR point cloud data into nice 1x1 square kilometer tiles. How did we do this? Let's first check the screenshot. The feature reader reads the point cloud files into FME. Then, a clipper is used to clip each point cloud file onto the 1x1 square kilometer tile extent. Then, a point cloud combiner transformer is used to merge the different clipped point clouds together, and finally an export to the LAS format is done. This is the standard point cloud format. To be able to do this, we must create a 1x1 square kilometer grid using the tiler transformer, and we looped over each tile using a workspace runner. There is still one issue. The feature reader is not able to read all 30 terabytes of data because it is way too big. Reading only the overlapping point cloud data works, but it is really slow because FME has to check for each input file individually what the extent is. If you have hundreds of thousands of input files, this takes a lot of time. And if you repeat this for each 1x1 square kilometer tile, it's not efficient. To solve this, we did it only once in a separate workspace and stored the minimum and maximum X and Y extents of each file into a CSV table. And using this CSV table, it's much faster to make a selection of which point cloud files should be read. Next step is the extraction of the 3D rooftop polygons from the tiled point cloud data. I will not go into detail over this step as this has nothing to do with FME, but after some investigation, we concluded that the NV LIDAR tool gave the best results in terms of completeness and accuracy. However, the outputs of this tool have several shortcomings. There is no spatial match with our Belmap building footprints layer, there are gaps and overlaps, and some false positive and false negative rooftop polygons are present. To solve all these issues, a long list of geometrical corrections is required. Again, this is something where FME proved to be very useful. Here on the left, you see a top view on a building with a hipped roof. The red rectangle is how the building is present in our Belmap building database. The black triangles and quadrangles are the outputs of the NV LIDAR tool. You clearly see that there are gaps and overlaps, and that there is no match with the Belmap footprint. We used FME to convert this situation to the cleaner version that you see on the right. The outlines match nicely to the Belmap 2D footprints, and all gaps and overlaps are removed. When doing the development of the FME models to do these geometrical corrections, we quickly discovered that the 3D component proved to be a real challenge, as most FME geometrical transformers are built to be run on 2D data. Often, the transformers do give an output, but those results did not always meet our quality requirements. Snapper transformers, however, did not have any difficulties with the Z component and do exactly what you would expect on the 3D data. But still, it's tricky to use them because they tend to make 3D polygons non-planar. The solution that we took in place to do the required geometrical corrections was to convert the input data to 2D using the 2D Forcer transformer, and then do all geometrical corrections you need in 2D, such as the area-on-area overlayer in the screenshot. And finally, you can use the surface draper transformer to convert your correct polygons back to the original 3D shapes. The last challenge I would like to discuss in this presentation is the huge amount of data to be post-processed. When run on Complete Belgium, the building detection tool extracted about 23 million of 3D rooftop polygons out of the point cloud data. At some point during the post-processing, we will also add walls, and that means that a multitude more 3D polygons will be added. At that time, we will have over 100 million of building polygons to be processed by FME. And we are lucky that Belgium is still a relatively small country with only 11 million of inhabitants. Imagine what we had to do if we would have to process France or Germany or even bigger countries like that. We also had some prerequisites. We did not want to have to use supercomputers, and we tried to do the work using only 2 standard virtual processing servers. And also, we want to make sure that we could produce an output for each single building in Belgium, since we did not want to lose any buildings along the way. So to summarize, this means that from 23 million 3D rooftop polygons, we use FME to create 9 million LOD2 building shapes. How did we handle this? We kept working on the 1x1 square kilometer tiles and used workspace runners to loop over each tile. Blocking transformers were avoided as much as possible. These transformers are always very slow. I did the maths, and a transformer, which takes only 1 second to run over a 1x1 square kilometer tile, which is still relatively fast, takes almost 9 hours to run over complete Belgium. The more blocking transformers you can avoid, the quicker your processing will be. In many cases, you can find a workaround in order not to have to use a blocking transformer. Workarounds are often complex and make the models less readable by others, but sometimes they are the only solution to make it work at reasonable speed. This is also the case for my last bullet point. FME is good at processing 99.9999999% of all buildings, but sometimes it happens that an awkwardly shaped polygon makes a transformer fail or even the model crash. If you have such a high number of polygons to process, it happens from time to time that you encounter this on one or a few polygons. But do never panic, there's always a workaround possible that allows you to avoid the error or crash and also lets you process those awkward shapes. But as said before, it makes the models much more complex, and of course it takes extra development time. At the very end of the processing, FME is used to create outputs in the cesium tiles format. This format allows for easy integration into different viewers, such as you can see here in the example. This viewer, for example, allows you to type in an address and will zoom to the building on that specific address. You see in the screenshot that the results of our processing look quite okay. But there are still several improvements possible. Some of them we are trying to tackle right now. Maintenance of this product is very important as we want the product to be kept up to date, so we also cover the new buildings. To conclude, I can say that FME is a good tool to process 3D data. Both point cloud data as 3D polygons. Many challenges of this project were related to the huge amount of data. To overcome this, we used styling and avoid blocking transformers as much as possible. After doing that, we were able to successfully generate Belmap in level of detail 2. And because life is better in 3D, our Belmap product also became better. And with that, I can end my presentation. If you would have any questions, please just ask. I also have put my email address here in case you want to contact me later on. Thanks a lot for attending.
Hi everyone, my name is Dean Howe, and firstly I'd like to thank SAFE for inviting us to talk at this World Fair this year. I'm going to be talking a little bit about juggling unstructured data between CAD and GIS, and just a few lessons learned along the way. So it's more of a, tips and tricks, some technical stuff. I'm not delving really too deep into actual FME, but just how it works and how it worked for our project. As I said, my name's Dean Howe. I'm an FME consultant. I'm a GIS professional. I've been in the industry for close to 30 years now. Worked all around Australia and around the world, and now working with Locus on a whole lot of FME projects. And thank you to Locus for also asking me to do this presentation here today. So today what we're going to be talking about is some JML, some juggling macro language. You're probably asking what is that? So I'll enlighten you shortly. We'll look into more detail about unstructured data, CAD and GIS. We'll look at using standards, quantity and quality. We'll look at performance tip that I'll give you, looking at custom transformers, multiple developers and the pitfalls of that, and just a quick conclusion, and then questions at the end. So hopefully that will make sense as we go on. So Locus started in New Zealand, but they've more than 10 years now helping organisations with their data challenges. I'm based in Adelaide in Australia, but the team across New Zealand, Australia, and helping organisations worldwide. There's a number of certified professionals which work with Locus at the FME desktop level, server and trainers. So we're here to help with all of that FME side of things. So, all right. So let's jump into the maths behind juggling. I guess it's probably one of those strange questions you've probably never been asked before. And you probably also go, well, is there really any maths behind juggling? But juggling and spatial data have a lot in common in that, we're talking about patterns and cycles and correlations of how data fit together. And so there is a lot of similarities there. But the maths behind juggling is actually quite complex when we think about it, because it comes down to how many balls or how many objects are we going to be throwing up, how many hands are we using? Are we just using one hand? We're using both of them, or we throw them overhead and we're doing whatever. And so are we using different size objects? I've seen people do watermelon and a tennis ball and all those sorts of things, and that adds to the different weights and different velocities and different heights and all those sorts of factors. So the maths behind juggling is actually quite interesting if you really wanted to look into it. Do jugglers really care? Well, some do, but most don't probably. And but there's probably some rationale in that jugglers probably should care a little, in that if you're just a occasional juggler, you probably don't really want to go into it. But if you get more and more experienced and want to do more, juggle more and more things, and then you probably want to be able to understand that maths behind it, so you can implement it in your mind more than anything else, and then get the mechanics. Do mathematicians really care about the maths of juggling? Well, I was actually surprised in that that there is an amazing amount of information out there from mathematicians studying juggling and the maths behind it, the patterns and all those sorts of things. And so yeah, a lot of mathematicians, look at that and see how that relates to different other things. And so if you're really interested and need some good bedtime reading, then search juggling and maths and you'll find lots on the internet. Do I care about the maths? Well, to be honest, probably not really. But for this, the thing I do care about is that spatial relationship. And the more you look at juggling, the more you look at spatial data. It's amazing, that correlation. And that's my passion, is in GIS and spatial location. And so in that case, I care about how they relate to each other. I care about what we can do with it. And it sort of adds a good synergy for my presentation today, how we juggle physical things and how we juggle data as well. All right, so let's look at JML, and I mentioned that before. I bet you not many people had heard of JML before, a juggling macro language. So if you look at on the left, it's just another variation of XML. And so if you have used XML in the past or have looked at an XML document, you'll see just the normal structure there, and so it enables programmers in this case to actually program how to simulate juggling. And in this XML, we've got the type of thing that's going to be juggled. So we're juggling a ball, but it could be something else. We're juggling what sort of path it's doing, how many hands we're doing, what position it starts, and all those sorts of things. And so there's a lot of actual information in that XML, but the main thing is when we look at it, we can, this sort of simple one, it's just juggling 3, and so the simulator actually is created from that XML, and how we can actually see that relationship between the X and Y events as they're moving along. All right, so that's a bit of fun leading up to what we're actually going to talk about today. And so we're going to talk about unstructured data, CAD and GIS. And my background's in GIS. I've used CAD a lot as well, but I've used GIS around the place. And I guess the main difference, and this is really just my definition, so there's, it's very debatable, but the difference between, a GIS is normally points, lines, and polygons with a database or attributes associated with those points, lines, and polygons. Whereas a CAD drawing doesn't necessarily need to have those attributes associated with the feature. So it could be just a raw drawing, points, lines, and polygons again, with some text on it, but that text has no real connection to the line except that it's drawn near it. Whereas in a GIS, we might use an attribute to actually label the polygon or label the line. Whereas we don't have to do that in CAD. We don't have to do it in GIS either, but it's more structured. So the GIS tends to be structured. We have a database there. We have a table where you define the features. Whereas a CAD, you can, in a CAD drawing, you can have lines and points and polygons all on the one layer, and you can have some text on that same layer. You can then have another layer which has the same lines, points, lines, and polygons. Whereas in a GIS drawing, we'll have some point layers, we'll have some line layers, we'll have some polygon layers, and normally the way you would do it is, all of the lines of a certain feature will be on one layer. So they might be spot heights as an example, and then you'll have a contour line, and then you'll have a lake or whatever as an area feature, and a river as a line, and all this. And they tend to be on different layers, so we can then analyze them a lot easier, whereas CAD doesn't have to be that way. So let's look at some examples of CAD drawings. Here we've got a drawing where we've got some arrows in there, and so we're going, all right, is that, we can sort of look at that visually and go, all right, the arrow points out to the 3 as an example, and that's a distance, and the 190, 57, 30 is a, we'd assume that's a bearing, but they could be on the same layer. And then we've got two different blue lines. We're going, all right, well, what does that actually mean? And we've got some text in brackets. What does that mean? And so it can, and spatially, where is that? It doesn't. CAD drawings don't have to be spatially located correctly. They may well be spatially dimensionally correct. So a 10-meter line is 10 meters, but it might be centered over Antarctica as opposed to over Adelaide. Here's another CAD example where we've got 27.92 and we've got a 4, and they're both sitting over the same line. We're going, all right, if I looked at that, I can see that the 4 relates to the lighter blue line because there's other 4s around it, and so I can make that assumption. But in that case, the 27.92 is actually closer to that blue line. So is it related to that? And so we actually have to do some tests. We have to go, all right, how long is that line in real-time space? Now, if it wasn't actually in real space, then how do we actually determine that? Whereas with the GIS, it's a bit more structured often. It doesn't have to definitively be, but here we need to do a lot more testing to actually make sure it's okay. Here we've got some other data. What does the underline under the text mean? Is it upside down mean anything? We've got a bearing in the middle of the road. What does that actually mean? What layer is it on? The 15.24 is telling us how wide the road is. Now, you might know those things, but how to program FME in this case out to figure that out is another thing. Orientation of a CAD drawing. Often in a GIS, the north arrow is connected to the data. So as you rotate, for a map, if you rotate the data, the north arrow will automatically rotate with it. With a CAD drawing, the north arrow is just another symbol on the drawing. It doesn't actually have to be connected to anything, and therefore you could actually get the north arrow pointing in one direction and the data being in a totally different orientation. So how do you actually figure out which is right, which is wrong, is that easy enough to do? Here we've got another example where we've got data over the top of each other, and the thing in CAD, we've got the concept, or certainly AutoCAD, we've got the concept of paper space and model space. And so model space is in that real world coordinate system, but it still doesn't need to be in the right geographic location. And then we've got the paper space, which is the how it should look when it's printed. So in this case, we've got text at lots of different sizes overlapping each other, and that's because in the paper space version, we're going to say, all right, only show things at a certain scale, only show these layers and whatever. Here's another example where we've got, this is actually a multi-story building, but the way it's been drawn is one of them might be correct, but they've then just done the copy of the base, moved it over to the side. So the second one's actually now spatially incorrect because it's not the property next door, it's the property on top of it. And so if we had that in a CAD drawing, we could turn off level 1 and just see level 2. And so, whereas within the CAD drawing, in this case, they've shown level 1 and level 2 in two separate spots. So it just makes it a bit more tricky to validate and to understand it. What can we do to actually make that unstructured data more structured? And this is where we can use standards. So here in Australia, we have the Australian standards, and I've just listed a random one there, the AS 1100, which is for technical drawing. Doesn't really relate to this project at all, but just to interesting if you want to read it. We've got Standards New Zealand, so they're the authority in New Zealand. So there's one SNHB3, which is just another technical drawing a standard. And then what you'll find is, depending on your industry, who you're actually drawing for, all those sorts of things. So here in South Australia, we have SA Water, and so they have requirements, a document called Requirements for Technical Drawings, TS0100. SA Power Networks, using a similar terminology for a technical standard, TS099. And, it just goes on. Almost any entity that is accepting a drawing, whether that be a CAD drawn drawing or a printed version of it, or an electronic version of it, will have a standard. And underlying that is probably the crux to how we actually can move from having data which is unstructured to moving slightly closer to being in a structured format. And a lot of CAD packages are now moving more and more closer to GIS. So you can actually add attributes to a line in AutoCAD as an example, but it depends on the use of it. So if you have no use to actually analyze that data, you're just drawing it because you need to lodge it to an authority, then why would you attribute it? And that's where GIS and CAD often are very different. GIS data is often used for analysis in a lot of cases, and map production and those sorts of things, whereas CAD tends to be, it's computer-aided drafting, and so it helps people produce their drawings for whatever authority that they're doing that for. So here we've added an extra ball into the simulation, and so using that standards, we could start to do a little more, but we're still going pretty slow, and we're still struggling to actually get it to match exactly the way we want to. But it's moved us a lot closer. All right, so we've now gone from a more technical side of things, some observations and analysis on my part. Now we're going to delve into some FME side of things, and quantity over quality, and that it's a really interesting thing, because if you read some safe documentation, they will recommend keeping the number of transformers in a model as small as possible, and I agree there 100%, but it doesn't always work. So in the project that I worked on, we had a number of workbenches that varied from, in this case, one of the smaller ones had 134 transformers, nice and simple, but 134, and it adds up really quickly once you start, you got data in, you do a bit of manipulation, format it a bit, and then output it. You very easily get 20, 30, 40 transformers just in a very short period of time, and then you start adding some to complexity. And so another one had 183, and then we jump to a huge step. We had 948 transformers in a single model. And so once we start getting up around that quantity, we start to then have performance issues. And our main model for this particular project had 3,869 transformers. And so can you imagine trying to manage that, trying to maintain that, trying to actually understand it if you had never seen it before. So huge numbers of transformers in a single model. And so understanding that quality and quantity, we're able to then juggle a little more. We're able to use the functions within FME to actually give us a better idea of what we're actually wanting to achieve. So one of the big things that I would say is that we actually want both quantity and quality. Quantity from a number of workbenches. So the more workbenches, the better in a project, in my opinion. Don't try to cram it all into one workbench, but we want quality in each of those. And so when we have that combination, and now it's not always possible, there's prime example 3,869 transformers. That's not a great number to try from a management point of view, or maintenance and all those sorts of things. That just makes it hard. So if we were to do it again, we'd probably break it down into more and more parts just to be better off. Here's a snippet of that model, the 3800 model, and this is just a snippet. And within FME, I press the extend button, and FME doesn't allow me to zoom in to the entire model just because it's so big. So you sort of have to get to this scale and then still pan and zoom or pan around to get to the other parts. And that's probably just a couple of hundred in that snapshot. But what we then did, and it's one of those performance tuning things as well, putting things in bookmarks and having bookmarks in bookmarks, helps you to understand what's going on, from a good authoring point of view and maintenance point of view. But it also helps it to, so you can run and test individual parts of that model. So you can just run that bookmark, or run that number of bookmarks, or run to that bookmark, as opposed to, run to an individual transformer. But yeah, it's crazy how big that got over a fairly short period of time. All right, so my performance tip for today and for this presentation is around attribute management. There's lots of data and lots of white pages and stuff on the FME forum about performance management, but this is one that is really stood out to me during this project. And at one point we just found that 3800 model was taking 15 minutes to run, which might not sound like a long time, because I know people who have models that take multiple hours to run. And when you look at the number of things it's trying to do, it's got 3,800 things to run through. You would think 15 minutes probably okay, but we started to go, it's starting to really, we noticed it getting slower and slower as we put more and more in. So we started investigating. And what we found is that when you're developing, it's very easy to just let the attributes flow from one transformer to the next. And very quickly, you've got a transformer that's processing 100 attributes, and it only needs 2 of them. And so we went through a process of actually using Attribute Manager, Attribute Keeper, and a number of other transformers in the project. And what we found is that 15-minute workbench went down to 2 minutes just by getting rid of attributes that weren't necessarily in the project. So we've literally got tens of the Attribute Keeper transformers throughout that big model, just culling attribute. We'll use the attribute and then cull the ones we don't need, and then set both Attribute Manager, Keeper, and the others. And so in this case, we've got just 3 attributes that we kept. We kept the AutoCAD space. That's an attribute from AutoCAD telling us whether it's in model space or paper space. The order that, so the tab order for us was its page, and then what business object we were processing. So they're just sort of things that we kept, and they flowed on. We did have some issues where, every now and then we did an attribute keeper and we didn't keep an attribute that was needed further on, and something would break, and we'd fix it up. But overall, once we finished those, then it gave us a lot more confidence that we could fine tune and the model would run so much better. So now, we're juggling more balls, keeping them in the air longer, and we're getting good performance out of it just through those simple things. And so if you're getting performance issues with your model, I would certainly recommend just searching the forums for performance, taking on some of those recommendations by SAFE and by the forum members, because there's so many of them there, and so many of them, just that fine tuning just helps you so much. The next performance thing that I certainly highly recommend is custom transformers. So when we're looking at the project in essence was taking in a CAD drawing and then validating it against a standard. So what we found during the proof of concept is we had all these little modules which were doing exactly the same thing. So reporting, mapping, validation, all doing those sorts of things. But we repeated the transformers. And so what we then did is had a process where we went through and actually converted all those repeatable actions into custom transformers. Now the benefit of that, and in the coming couple of slides we talk about multiple developers. The benefit of having those custom transformers is that they can be then shared between workbenches. They can then be shared between developers. So if your one developer is working on one workbench, but they might just, what they need might be in that custom transformer, they can just edit that custom transformer or utilize that custom transformer and not bother that other developer. So the benefits of custom transformers, consistency of programming. I don't know how many times I've seen developers, where they'll misspell something, or, the formatting of one part of the report is different to the other, and you're just going, why aren't you guys being consistent? Now, by using a custom transformer, they only have to do it once, therefore actually remove that consistency problem, because all of the variables are done in one spot. Testing. The other great thing about custom transformers is that we can test in isolation. So you can publish that custom transformer, open it up in a new workbench, test it to your heart's content, and you're actually not affecting the other developers, the other testers, or anything like that. Maintenance. So if we want to look long term, often the people doing the development aren't the people doing the maintenance. So we have that big model, and I dread the person who's going to have to maintain that, because it's just huge. I wrote a document when it was at about 1,500, and that document was multi-tens of pages, just trying to explain how the model worked. So from a maintenance point of view, custom transformers make it really easy, because you can, once again, isolate that bit of programming. You can if you go, oh, why is this not working? And then look in the transformer, fix the transformer, publish it, and then so you don't have to go and publish the whole thing again. It also speeds up development. We talked a little bit about that already, that we have multiple developers utilizing the one custom transformer, and still can only have one developer changing it, but we can have multiple developers using it, and that becomes really quite efficient when we want to do our when we're getting to big projects which have lots and lots of developers. So here are a couple examples. Map generator we created. Now we've literally got hundreds of these in that big model. So the actual transformer number is probably so much bigger than 3,800, because we're looking at hundreds of these as well, which might then have lots in it. So we have a status one to make sure that the statuses are consistent. Have you seen that where someone will type just type a attribute incorrectly, and then that flows on, and you go, why isn't this working? Well, using a custom transformer, the status is always the same. Base map builders, so the same base map is being built all the time, and that's what we were finding once we were doing the reporting. We were going, why isn't this part the same as this part? And so once we created the custom transformer, those base maps were spot on all the time. All right, so we're now able to juggle a lot more balls in the same amount of time. We're now more confident in what we're doing because of all those pieces that we're putting together. All right, so I did just briefly touch on this, but I thought it's one of the last things I'm going to talk about, but and that is versioning within FME, and versioning with FME Server. I'm a big fan of that. It helps to keep the models in when they're published, and so it's going in. But The biggest problem I see with FME, it doesn't allow multiple developers to work on a thing at one time. Now, you probably come back to me and say, well, why would you want to do that? But what we found is that when we were trying to prioritize functionality within the project, we also had to figure out the workload for individual developers. So we had to make sure that, you know, developer 1 had enough work over here and developer 2 could do over there. And sometimes it was just really difficult. And you might end up with a developer just sitting doing nothing, and that makes it hard. So when we do that custom transformer type of thing, we can actually then say to those different developers, all right, you work on this custom transformer and that'll need to do this, so I can then use it in my model here. And we then can do that. So versioning with FME service, some organizations will use, you know, GitHub and those sorts of things, but it's a real tricky juggle with multiple developers, and we always want to try and see what we can do to improve that. And I certainly think that custom transforms is one of those ways. So it's just another little graphic. Now we're getting multiple people involved in the whole process. We're having to juggle that data, juggle those processes, juggle those workbenches for everyone to use. All right, so I appreciate your time today. We'll come up shortly for some questions, but enjoy your time juggling the data, and you know, look up all the maths on juggling online. You might be surprised. All right, so thank you, and I thank you to SAFE as well for giving us the opportunity to be here today.
Hello and welcome to FME Server Apps and Beyond. My name is Dennis Wilhelm, and I've been working as a software engineer at Conterra since 2015. In order to show you what FME Server Apps are all about, I figured let's start with a demo right at the beginning. So if I move over to the FME Server web interface, what we can do is we can go to FME Server Apps, click Build Workspace App, and by simply filling out all of these information like name, title, and description, we can create the base information for our app, and now we only need to specify which workspace should be used. And in my example, this would be my app demo repository with the download data workspace. I could also specify which parameters should be used or should be visible in the app. For example, I have a parameter that shows me all of these output formats. And I can also specify different images that could be used, for example, as a browser icon, heading background, heading logo, and so on. So let's upload a few images. For my heading logo, I'm going to upload a specific file, and I'm also going to provide a footer logo. And now if I click OK, I get an URL that's basically pointing me to my demo application. So that's all it takes to create a small application. And as you can see here, I can specify my format. I can also choose a map extent. Let's choose something like that. And if I click OK, the workspace is running. And in this specific case, I'm getting a download URL to download my data. Once your application is up and running, you could integrate it as an iframe into an existing website, which could basically look like this. So we have a website, and your FME Server app seamlessly integrates as if it would be part of this whole website. So let's go back to the slides. What we have seen so far is basically a way to create clean and easy to use websites, well, as they are called here, apps, which are based on published parameters of a workspace and based also on the services data streaming, data download, and job submitter. So you could basically stream data. For example, you can simply output an image that would be shown right away. You can provide a data download, which would be a zip file containing all of your data sets, or you could run a job submitter workspace, which would simply execute as a normal workspace would. You can specify various images and texts to create a custom design. And if required, you can also specify that all of your users should be authenticated to use your app. If you have multiple apps, you could also aggregate all of that together into a gallery, which would basically show multiple apps on one side. So why do we even need FME server apps? Basically, you should know your target audience. And I guess most of us are GIS professionals using FME desktop or FME server for quite a long time. And we are not easily intimidated by a workspace as seen on the slide here. We could also have workspaces that are basically running as automations, which don't need a user interface at all. But the last bullet point here, self-service, is where FME server apps are really shining. So if you have a target audience that isn't experienced using FME server or FME desktop, then you don't really want to make your workspace or your interface really complicated, but rather what you want to have is you want to have an intuitive user interface that's easy to use and doesn't really need training or anything else in order to be successful. And what you can also do is you can integrate apps into an existing website, and therefore a user wouldn't even know that he is currently using FME. But what if I need more than that? So luckily, FME server provides a REST interface, which allows you to do almost anything you can do in the original FME web interface. So you can run FME server workspaces, but you could also have a look at all the different existing users, workspaces, repositories, and all of that stuff. So what we did is we did a full integration into a WebGIS. And the main goal for that is basically that you can interact with already existing data in your application. For example, you could use data that's already existing on a map for your process, or you could visualize results in your application, for example, vector data on your map. This allows for more complex workflows, which might even include multiple steps. So for example, you could upload data, edit all of this data that you have uploaded. So for example, geometries, attributes, and all of that stuff. And later on, you might want to integrate your edited data in your database, or you might want to provide a download for the user again. So I guess it's time for another demonstration. This demo shows our product called MapApps. MapApps is a highly customizable WebGIS for which we created a plugin to run FME workspaces. The FME output can be understood by MapApps, which allows us to display the result on the map. We noticed that one of the most important steps for a broader audience, at least, is to provide some sort of input validation. Therefore, our upload widget, which you can see here, can be configured to restrict certain file types. In this specific scenario, we are allowed to upload shapefiles, zip files, and all of the shapefile extensions and any sort of file size. So let's upload something that isn't allowed, just to make sure that that's working. Okay, so as a user, I now understand that I'm not supposed to upload a file like this, and I'm not frustrated later on if my process doesn't work. So now I'm going to upload a file that is allowed, which is just a shapefile. And in this case, I already know that my shapefile consists out of polygons. And in the next step, I can specify my published parameters, which could be color, for example. And once I run my workspace, FME handles the data processing to make sure that we have a format that MapApps understands. I could now go ahead and upload even more data, maybe with another color to make sure that I can distinguish between all of them. And the nice thing here is that now that I have all my data in MapApps, I can fully work with all of that. So I could provide, for example, I could have a look at all of the data in our result center, which is just a table view of all of the attributes, or I could even go ahead and start to edit the geometries of individual features. Once everything is as I expect it to be, I could also go ahead, select data again that I might want to download. So in this case, I can select a few entries down in our result center again and make sure that I use another workspace, which could also be used to specify which parameters or which attributes I want to download. And in the next step, I can specify my download format again. From all of the presets, I specify my FME workspace. And once I click Start Transformation again, I can download the result as a zip archive. As I mentioned, this is a full-blown WebGIS, which could also be used for many more functionalities. For example, you could create custom queries to search for your data and all of that stuff. But that's enough for this demonstration. Since we're using FME in the background, we can also do more advanced stuff like pre-processing data to provide more meaningful information. So in this case, I'm uploading a DXF file again, which simply consists out of a few point information, and I can specify drive time polygons for 5, 10, and 15 minutes based from these point locations. And that basically shows us how the power of FME can also be used in a simple import mechanism to provide more meaningful information, which wouldn't be possible in other applications. All right, let's go back to the slides. So what did we see in this talk? It's really easy to create simple and intuitive FME server applications, FME server apps, which can be basically clicked together in 1 or 2 minutes. And they can even be used in more advanced applications by providing them as iframes or simply by creating a link to these applications. And for most use cases, these are perfectly fine. They create a more easy to use interface than the default FME server interface would, and therefore allowing us to create applications for a broader audience. If you need more functionality than that, you can easily use the REST interface if you know how to use it and if you are used to developing your own applications, and therefore the possibilities are basically endless and can be used to create custom integrations, as you could see in our application, which allow you to create any sort of application that might want to use FME processes in the background without showing any of the complex process to the actual user. So if you like this talk and you want to know more about FME, map apps, or our integrations, feel free to contact us at fme@conterra.de, visit our channels and all of that stuff. And have fun with the next talks and hope we see you soon. Bye.